Hi, welcome back to VRC Smart Edu channel, and here with class 11 physics series chapter 8 gravitation. This is part 5 video of this chapter. So in this part we are going to deal about the satellites. Okay, so before entering into our today's session, let's recall our previous session. So our previous session was based on escape velocities and few definitions about the gravitation. So if you have not watched our previous session, the links are provided in the description. You can go and check it out. So come on, let's solve today's question based on previous day's discussion. Right? Okay. So the question states, the ratio of masses and radii of two planets are given. This is the mass of ratio of first planet and this is the mass of ratio of the second planet. What is the ratio of their escape speed? Okay, so what we learned about the escape speed, what is the formula that we learned about the escape speed? Escape speed VE is equal to 2g m by r, right? 2g under the square root of 2g m by r, right? This is what we learned in our previous session. And they are given that your first planet's ratio of mass and radii are given. Your second planet's ratio of mass and radii are given. Then how do you express it? So VE of our first planet is given under the square root of 2g. First given is mass, second given is radii. So our mass is going to be just 2, right? By our radii is 3. Then our BE2 will be equal to under the square root of 2 under the square root of 1 second. Under the square root of 2g, here it is 4. So you will just substitute 4, right? 4 by 9. Now, what we need? We need is VE, that is what is the ratio of the escape velocity. So our VE1 by VE2 is what we need, right? So now how would we get it? Square root of 2 2s are 4. We get 4g by 3 divided by square root of 8g by 9, right? So your VE1 by VE2 will be under the square root of 4g by 3 into 9 by 8g. So your g and g can be cancelled. 4 2s are 8, right? And 3 3s are 9. So you will get your VE by VE1 by VE2 is equal to under the square root of 3 by 2. So you have to express it in the form of ratio. So therefore the ratio is square root of 3 is to square root of 2. So this is your required ratio of the escape speed at the surface. Okay. So the ratio of the escape speed at the surface is square root of 3 is to square root of 2. Clear? That's all. So now we are moving to today's topic. So today's topic we are just dealing with satellite first, right? So satellite. First let us try to know what is satellite. So satellite is a body which continuously moves around the bigger body. So here, if it is a satellite that is revolving around the earth, then it is called as a bigger body is nothing but the earth. So some body will be bigger body. So satellite itself is a body that is revolving continuously around a bigger body. So if it is revolving around something, that is called as a satellite. So we know it really well that our moon is our natural satellite. So we can also make the artificial satellites and send to the earth. So one of which the first Indian satellite was The artificial satellite we made in India. So the first Indian satellite was Aryabhatta. Aryabhatta. So the first Indian satellite was Aryabhatta. So it is an artificial satellite. So only the moon is our natural satellite. We can prepare artificial satellite and we can send it to the space. Okay? Right. So what is orbital velocity of a satellite? Orbital velocity is a velocity that is given to the artificial Earth satellite a few hundred kilometers above the Earth's surface. So it may start revolving around the Earth. Okay? Okay. So what is orbital velocity? Let's see in detail. Okay. So orbital velocity. Now imagine this is our Earth's surface. Okay. So what we studied about the escape velocity, we will be giving some velocity to the satellite from the Earth's surface, right? So that the satellite will move out of the Earth's surface to the space. It will move to the space, so it will be escaping from the gravity. That is called as escape velocity. So after it moves out of the space, it goes a few hundred kilometers above the space. Okay. So from there, what happens? It need to revolve around the Earth. It need to go revolve around the Earth in this way. So it need to revolve around the Earth. For that purpose, if we are giving any velocity, for the purpose after it is going few hundred kilometers above the Earth's surface, it need to revolve around the Earth. Okay, so if it need to revolve around the Earth, we need to give some velocity for that purpose. So if we are giving some velocity for that purpose, then it is called as what? Then it is called as orbital velocity. Then it is called as orbital velocity. So our orbital velocity is also called as what? Critical velocity. Our orbital velocity is also called as critical velocity. Right? Orbital velocity is also called as critical velocity. Clear everybody? Okay. Now let us see a derivation based on expression for orbital velocity. Okay. Okay. So how do you express this? Now, what I'm going to do is, let us consider the orbital velocity of the satellite. Orbital velocity of the satellite be V naught. So V naught is the orbital velocity of the satellite. Now, the satellite is projected above the Earth's surface. For example, this is our Earth. Okay, this is our Earth in the sense. So the satellite is projected a few hundred kilometers, I told, above the Earth. So if this is the Earth's surface, what will be the radius of the Earth? This will be the radius of the Earth. This part will be the radius of the Earth. But the satellite is going few hundred kilometers above the Earth's surface, means here the satellite is present. So this distance we are going to consider it as what? This distance we are going to consider it as h. This distance we are going to consider it as h. Okay. So this is the distance. We are considering it as h. So now what I am going to do is, now at this point we will be giving our orbital velocity. So what happens? Our satellites start to move around the Earth's surface, right? Our satellites start to move around the Earth's surface. So this is called as line what I have drawn now. This is called as circular orbit of the satellite. This is the circular orbit of the satellite. Right. So now we have to take in the orbital velocity as v naught. So now let's derive. Okay. So what is our gravitational force? What is our gravitational force? Gravitational force F is equal to G capital M small m by r square, right? So what is our r here? Our r is equal to, our radius is equal to r plus h the whole square, because this whole will be our radius. So here it will be r plus h the whole square, right? So our r is r plus h. Okay, our r is r plus h. So here r square, right? So r plus h the whole square. Okay. Next, what we are going to do means this, we are going to consider it our first equation. Next, since it is revolving around the circular orbit, right? So since the satellite is revolving around the circular orbit, since the satellite is revolving around the circular orbit, so what we are going to do means we are going to use here centripetal force. Centripetal force. What is our centripetal force? Centripetal force is equal to mv square by r, right? So what is the centripetal force for the case of the satellite? So your centripetal force is equal to mv square by r plus h, right? So going to consider it as second equation. So first equation also you can see here it is f. Second equation also you can see here it is f. So from 1 and 2, what I can say? From 1 and 2, I can say that your mv square by r plus h will be equal to g capital M small m by r plus h, the whole square. So now your mass and your mass can be cancelled. Yes, r plus h and 1 r plus h can be cancelled. So this is your V naught. Simply you can just name it as V naught here. Here it is V naught, because it is orbital velocity of the satellite. So we can consider it as V naught. So your V naught will be equal to under the square root of g m by r plus h. So this is your V naught. So this is an expression for your orbital velocity. So from this expression, we can say the orbital velocity depends upon. So from the expression given above, we can say that our orbital velocity depends upon. So first it is depending upon the mass of the earth. So this m stands for what? This m stands for mass of the earth. Mass of the earth. Then it is dependent upon the radius of the earth. R stands for radius of the earth. Radius of the earth. And number 3, it is also depending upon the height of the satellite above the earth's surface. Height of the satellite above the earth's surface. Clear? Right. Now let's move to the next topic. Our next topic is about the communication satellite. So what is all about the communication satellite? So communication satellite is also an artificial satellite that is moving in the circular orbit around the earth. So it is also moving in the circular orbit around the earth. It is rotating. So it is in the same sense the rotational of the earth and having the same period of revolution as a period of rotation of the earth. Okay. So the geostationary satellite is also called as communication satellite. Our communication satellite is also called as geostationary satellite. So that is about the communication satellite. Now we have various uses of communication satellite. So what for our communication satellite is used? So our communication satellite is used for sending TV signals over the larger distances on the earth's surface. We are using it for telecommunication. We are using it for weather forecasting. So we are identifying the weather, right? All is because of this communication satellites. These are some of the uses of communication satellites. Clear? Okay. Now let us see the very most important topic. It is very easy to understand. So weightlessness. So the topic now we are going to deal with is about the weightlessness. So what is all about the weightlessness? Let us see with an help of an example. Okay. Okay. So the gravitational force by which we are attracted towards the earth's surface. So because of gravity, if we are attracting towards the earth's surface, we call it as weight, right? We call it as weight. We are attracted to the center of the earth. Okay. So we are attracted to the center of the earth is because of our weight. Now, let us take an example. Okay, let us consider an example. I'm just going to say the example. Just imagine it. So, we are considering an astronaut. We are considering an astronaut. Now, what this astronaut is doing is, he is standing on the surface of the earth. Okay, first case, he is standing on the surface of the earth. So, when he is standing on the surface of the earth, what happens? The gravitational force of the astronaut will act on him, right? Gravitational force will act on the astronaut, right? So now the astronaut will give some weight. He will exhibit some weight, right? So he will exhibit some weight. Similarly, when he exhibits some weight, the opposite, what happens? Opposite direction, the force will act. Okay, equal and opposite reaction we say, no? Opposite direction also the force will act. Due to which the astronaut can able to feel his weight on the earth, because both the directions some force is acting. Here also some force is acting, here also some force is acting, so it is getting neutralized. So he could able to stand on the surface of the earth and he could able to just feel his weight on the surface of the earth. But now the astronaut, same person, is moving to the moon, is moving to some space. Oh, he is just moving to, just let us imagine he's moving to some spacious area. He's moving to some space. Then what will happen? When he is moving to some space, what happens is, his acceleration as well as the satellite's acceleration both will become same. Both will become same. So he's not going to stand on the ground. So ground is not going to produce any force. Therefore, the force produced is zero. So what happens is, he couldn't able to feel his weight. As a result, in the second case, when he is in space, he couldn't able to feel his weight. Here he can able to feel his weight, but here he couldn't able to feel his weight. Okay, so that is a difference. So where he couldn't able to feel his weight in the space, right? So that case is called as weightlessness. Okay, that case is called as weightlessness. So astronaut will have a feeling of weightlessness. Weightlessness is nothing but, it is nothing but no feelings of his own weight. Weightlessness is no feelings, or instead of using the word feelings, you can just say no sense. No sense of his own weight. Of his own weight. Right? So that is called as weightlessness. Clear? Right. So most commonly, the people who go for space for the first initial period of time, they will face weightlessness in the space. So at that time, they will be having the adaptation syndrome. So they will be experiencing, most of the astronauts will be experiencing this case in the initial period of traveling to space. So that is nothing but adaptation syndrome. Adaptation syndrome. So this adaptation syndrome is also called as space sickness. This adaptation syndrome is also called as space sickness. Clear? Okay. Thank you so much. So now let us move to a question based on the topic that we have discussed. Okay. What will be the mass of an object under free fall if at the Earth's surface it weighs 100 Newton? Your G value, you have to consider your G value here as, this is nothing but 10 meter per second square. So that is what, okay, you have to consider your gravitation here as 10 meter per second square. Now, so at free fall, at free fall, you can say that weight becomes zero. Weight becomes zero. You already know there is a lot of difference between weight and mass. Mass will never change. We will be having the same mass throughout wherever we go. But weight will change when your gravitation changes. So gravitation of the earth, when we are at gravitation of the earth, we will be having different weight. When we go to different planets, we have different weights because the gravitation changes, right? So weight depends on gravitation. So at free fall, the weight becomes zero. So now when I explained what is weight, right? So that not means that your mass is becoming zero. You have certain mass. If you are 65 kgs or 75 kgs, you will be at the same mass. But your weight will change in case of gravitation. Okay? At free fall, weight becomes zero. But your mass remains same. But your mass remains unchanged. Clear? So your weight changes but mass remains unchanged. So at that case, they have given that the Earth's surface, it weighs 100 Newton. So your mg is equal to 100 Newton. So here your mg is equal to 100 Newton. So already we know that our g is equal to 10 meter per second square. So your m is equal to 100 Newton by 10 meter per second square. So 10, 1, 0, 1, 0 cancel. So your m is equal to 10 kg. Your mass is 10 kg.